So welcome everyone to the second exam review for Organic Chemistry 1, GeoChem Live review. So without further ado, we'll just jump right into it. I have like 7-ish problems that I've picked out to hopefully span the stereochemistry related topics, and then stopping at the end of so to cover stereochemistry and SN1, SN2, E2, and E1, the individual reactions, as well as picking between them when presented with a reaction. And then kind of like a little bonus problem at the end, it's a synthesis problem, which you may or may not have gone to in your course yet, but eventually you will get there. So we'll kind of work through that together. If you were hoping for some Grignard content or some alcohols related stuff, don't worry, I'm having a third, an OChem 1 third exam review that will happen sometime in mid-November. Be on the lookout for that. It'll have maybe more of the content you were hoping to find, but this is stereochemistry and then substitution, SN1, SN2, and elimination, E2, E1 reactions. So without further ado, let's go. Okay, so as you can see, I've pre-populated the board so you don't have to watch me struggle through writing all of this. So this first problem, the first of 7, is going to deal with a series of true, false, and then one prompt question right here. So let's, take it one step at a time. For letter A, this statement that we have to evaluate as either true or false says a structure with 2 stereocenters and no internal plane of symmetry will rotate the plane of polarized light. Now, I on purpose made this as wordy and definition geared as possible because sometimes these true and false questions aren't meant to be hard, but if you don't truly understand definitions of terms, especially with stereochemistry, it's easy to get tripped up. What this is saying is if a structure has 2 stereocenters and no internal plane of symmetry, which if it helps you to draw something out, you could even draw out something like this. We have 2 stereocenters. There's no kind of dotted line I can draw to cut this thing in half. That means, and the statement says, the structure will rotate the plane of polarized light. Now remember, if we are chiral, we have the following properties in a structure. We have a non-superimposable mirror image, aka an enantiomer, and we will rotate the plane of polarized light. So because this structure has stereocenters and does not have an internal plane of symmetry, we are actually chiral. We are in fact chiral, which means, yes, we will rotate the plane of polarized light. So this first question is true, or statement rather, is indeed true. Now let's go on to B. If a compound has a non-superimposable mirror image of itself, it is achiral. Now, based on what we just talked about above, if you are chiral, you have the following 2 properties. You have a non-superimposable mirror image, and you rotate the plane of polarized light. I was trying to be a little sneaky here. This sentence almost leads you to think that what's naturally coming is if a compound has this, it is chiral, but I actually said it is achiral. So achiral structures don't have a non-superimposable mirror image. Achiral structures, you can just, however it's drawn differently, you could eventually flip it around and line it up completely on itself. So this is actually false because if a compound has a non-superimposable mirror image, we're actually chiral, not achiral. Now for C, provide an example of a valid mesostructure. Now, again, remember, this really just comes down to knowing your definitions. Remember that a mesostructure is a structure with an internal plane of symmetry, or a plane of symmetry. So if you drew something like this, you could come up with a whole bunch of things. And you could put, if I came up with something like this, I could draw a dotted line like this. If I drew something like this, this has an internal plane of symmetry. As long as you draw something that's symmetrical, it counts, right? That's all we need for a mesostructure. So you can have whatever example you come up with, as long as you can draw a dotted line through it and you can fold one side over on the other like a sandwich, you're good to go. D, a structure with 3 stereocenters has 8 stereoisomers. Okay, now I feel like this is more like a little niche type of question, but I'll give you 2 different explanations here. So if you explicitly learned in your class, you can calculate the total amount of stereoisomers for a structure by doing 2 to the n power, where n is the number of stereocenters. So 2 to the n, if we wanted to just do 2 to the third, 2 times 2 times 2, right? 2 times 2 is 4, 4 times 2 is in fact 8. So this is a true statement. The other way you can think about this is if at every stereocenter, you know you have 2 choices, R and S, R and S, R and S. This explains why this rule works. If you remember some rule from statistics, you can get the total number of combinations or like results for a given thing if you just kind of take your total options and multiply them all together. So that's why you do 2 times 2 times 2. Because at every stereocenter, we have the option to either be R or S. 2 options times 2 options times 2 options gives you 2 to the third. Okay, that gives us problem 1. So I'm going to erase this as I most quickly can, and we will roll straight into problem number 2. But I wanted to make sure we talked about those types of stereochemistry wordy questions, because I feel like stereochemistry can be a bit wonky in and of itself. The minute you start putting a bunch of sentences and everything into the mix, that's when things can get, it can hurt the brain. Okay, let's move on to problem 2. Okay, what do we have going on here? Okay, so in this next problem, we are going to identify the relationship between the provided pair of molecules. I'm going to give you, there's going to be 3 of these, and I'm going to give you 2 structures, and we're going to have to figure out if they are the same, if they are constitutional isomers, or if they are enantiomers or diastereomers. Okay, cool. Let me draw these really quickly. When I get these on the board, we'll talk a little strategy, and then we'll also just go ahead and rip right through them. Chlorine. We got. And then last but not least, down here, all right. I got one more over here. I'm gonna switch to another marker because this one's dying on me a little bit. I should have given myself a little bit more space, but it be like that sometimes. Put these over here. Almost there. OH. H. All right. Here we go. So, gang, my approach to these types of problems kind of take it in 2 ways, in my opinion. First, evaluate whether or not what you have are, the same molecule / the constitutional isomer. Because if you don't have to assign RNS, try to figure that out ahead of time. Try to work smart, not work hard. So in this first problem up here, we can see we have 6 carbons. We have 6 carbons here. But the key is, before we even start assigning, stereochemistry, or maybe try to convert these chairs into flat, cyclohexane molecules to assign RNS, one major thing to note and one thing to look for is if you have substituents on a molecule, just make sure that they are all attached in the same position. Because you can see this is certainly, we have the same number of carbons, bromines, hydrogens, etc. However, I think what you can see here is on this structure on the left, we have a 1-3 relationship between the bromines. However, on this one over here, we actually have a 1-4 relationship with the bromines. So at this point in time, we actually don't give, we don't care at all that this could be R or S and this could be R or S. And we don't care what it is on the other side, because we're not dealing with a stereoisomeric situation. Stereoisomers are when you have stuff hooked up in the same positions, but they're arranged in space differently, right? You have R in one place and S in another. What we have here is just 2 molecules where our atom-to-atom connections, we have them all, they're all equal on this side and this side, but they're just hooked up differently. So this is a situation where this pair right here, we have, this is a structural, or what we can also call constitutional isomeric relationship. Okay, so constitutional isomers for the first one. Okay, now down here, these two, let's kind of maybe take the same approach. So you can see we have a carbon in the middle, we have an isopropyl group, we have a bromine, we have a chlorine. Okay, so we know no constitutional isomerism going on here. Let's, we have the same groups. They could be arranged differently though. So let's assign stereochemistry to figure out, is it the same? Are they enantiomers? We won't have diastereomers here because we only have one stereocenter present, okay? So let's start with the left. Now remember, this is and this is why I included this problem, this is a Fisher projection. So remember, there's a kind of, the convention with Fisher projections is that from a given center, the bonds that go up and down, north and south, they are like dashes. They are, if you are looking at me, they're facing towards the board or through the board. They're away from you. On the other hand, the bonds that go left and right, picture them almost as arms that are coming out to hug you. They're coming at you. They're coming at the camera at an angle like this, okay? That matters because remember, when we assign RNS, we need to understand if our lowest priority group is facing us, coming at us as a wedge, or coming away from us like a dash. So if we take this situation right here, believe it or not, our lowest priority group here is the methyl group, because bromine and chlorine, way heavier than the carbons that are attached here and here. And then since we have a tie between carbon and carbon, we go to the next group that is attached to these carbons. And here we only have 3 little measly hydrogens, but over here we have, a whole CH3, a whole CH3. So our lowest priority group is the methyl group right here, right? I'll put a little 4 next to it. Not that we usually draw the 4, but lowest priority group is on the vertical. It's actually facing away from us. So when we assign RNS here, we can just do it straight up and just trust that what it is what it is. Now, moving on to kind of assigning our priority for the rest of the groups here, if you consult the periodic table, bromine is by molecular weight the heaviest, chlorine comes next, and then this isopropyl group over here will come in third. So remember, this is where we get to kind of break out our driver's ed knowledge. We kind of follow in the direction from 1, 2, and 3. We turn the steering wheel to the left. We don't use L, so this is actually S. Sorry, I almost confused myself. S. Now let's go over here. We know lowest priority group over here is the methyl. Now remember, what that means is it's different here. We actually have it now on one of the, on the right-hand side, it's a wedge. So what we can do here is we can assign stereochemistry, but to keep our convention, we'll have to flip whatever result we get. We'll take the opposite because our lowest priority group is facing towards us. If we take the opposite result, that's as if we had done the work to kind of rotate bonds and make our lowest priority group facing away from us. So priorities don't change here. First with bromine, second chlorine, third isopropyl. So here's the kicker. Going from 1, 2, 3, we look like we're again turning the car left. But remember, we have to take the opposite because our lowest priority group is facing towards us. So we look like S, and we're going to cross through it, and we are actually R, okay? Comparing the two, we only have one stereocenter. We have S, one S, and we have one R. Since we are completely opposite in terms of the configuration, that means we have a non-superimposable mirror image of each other. We basically have a left and right hand pair. These, my fellow geochemists, are enantiomers. Cool. Now, I'm going to go ahead and make some room here because we're going to have to do a little bit of work on this bottom one. I left the most involved one for last. Okay, so down here, we have, what you can see, 2 stereocenters. No other carbons anywhere else that would qualify as stereocenters. So real quick before we dive in, we have I'm really glad I did this. I actually drew this incorrectly. This should be a hydrogen. I'm really glad. I was going to say, let's compare what's attached on both sides to make sure they're the same. I made a mistake. Let me just double check this before we dive in. OH, NH2, NH2, OH, perfect. Okay, so NH2, OH, H, NH2, H, OH. So every carbon has a hydrogen, an oxygen, and an NH2. And that is, in fact, the case. So we're not dealing with, any type of constitutional isomerism. Let's assign stereochemistry and figure out, do we have enantiomers, the same molecule, or diastereomers? So let's start over here. If we take a look at this carbon right here, what we can see is we have our lowest priority group, the hydrogen, is coming at us. So we can assign and take the opposite. If we're going to assign a priority, oxygen is the heaviest, because if we look at the periodic table, we have carbon, nitrogen, oxygen. So oxygen is the heaviest. Nitrogen comes next. And then over here, we just have a carbon. Picture this as a carbon with a bunch of stuff on it. But carbon's the first molecule, the atom we're considering off of this stereocenter. So if we go like this in the direction of 1, 2, and 3, we look like we're turning the car to the right. We look like R, but we're actually S. Okay, cool. That's one. Now over here, I'm going to erase these little numbers. I included this one to make it a bit annoying. I'm sorry. On this carbon right here, our priorities don't change at all. However, I did the annoying thing of putting our lowest priority group on a straight line. You have 2 options here. If you can do the mental gymnastics, you can kind of literally take on this perspective and make your head level with your piece of paper or whatever you're writing on and look at it like this and visualize the rest of the bonds. Because if you look like this, the hydrogen's away from you. That hurts my brain. I don't know if I would get it correct all the time, so I like to use the double switch here. The double switch is you switch a pair of 2 groups one time. That inverts the stereochemistry. Then you switch another pair. You recover the stereochemistry, and in the process, you can be clever and put that lowest priority group on, a dash to be away from you. So what I'll do first is I will switch the hydrogen and the OH. I'm just going to kind of like redraw this like up here. I'm going to make this an R group over here. So what I'll do now is I have the OH, the hydrogen, and the nitrogen. So this was our first switch. I cannot stop here. I have to switch one more time because I've inverted the stereochemistry. So I'll switch one more time. Let's just switch the no, let's not do that. Let's switch the OH and the NH2. So let's do the R group. Let's do the NH2, the OH, and the H. So you can trust me on this. These have equivalent stereochemical configurations. We've just done the double switch. We've done a life hack to avoid having to do the mental gymnastics. So let's assign stereochemistry. OH comes in first, nitrogen second, R group third. It looks like I'm turning the wheel to the right, and since our lowest priority group, the hydrogen, is facing away from us, it is in fact what it looks like. This is an R. Stereochemical configuration. Let me just double check that really quickly. Yep. Let me just make sure, because I have something written down here, but I was doing this when I was pretty sleepy the other night. So there's a good chance that I may have messed that up. Okay, cool. Let's keep going. Now, over here. Luckily, we have both of the hydrogens facing away from us, so not a big deal whatsoever in terms of having to do the mental gymnastics that we were just doing before. So what we can do here is oxygen gets the highest priority, nitrogen second, this carbon R group over here third. For this carbon on the left, I can do one big thing like this, turn it to the left. It looks like S, and it actually is S. Erase this. And then over here, what we can do is say that hydrogen facing away from us, maybe you even noticed that it looked eerily similar to when we just did the double switch right there. OH, NH2, R group. We're going this way to the right, and our hydrogen is facing away from us. So this is in fact R. So now what we can do is we can compare our stereo situations right here, and this is actually the same molecule. And, you know, if you were smart enough to catch on in the beginning, which I think when I was designing this problem and I wasn't too clever / I was a little tired the other night, this is actually meso. So all of that to say, since there is an internal plane of symmetry here, there is no possibility for there to be an enantiomer, diastereomer, etc. There will always be a situation where, however you redraw this, as long as it's drawn correctly, you'll be able to rotate bonds such that you will be able to, there won't be a non-superimposable mirror image, is what I'm trying to say. Okay, cool. That does it for problem number 2. All right, moving on to 3. So for 3, we have 2 parts. I'm just going to whip them up really quickly. Oh, wait, let's do this. Whoopsie. Okay, so this is kind of like A, if you will. Let me just whip up B, and then we can just dive into both. Nope. Okay. So what we want to do for A and B is we want to identify one of two reactions. In A, we're actually more interested in the faster reaction. In B, we're interested in the slower reaction. So this is, a comparison type of thing. So let's identify it and then give a follow-up reason as well. So if we take a look right here, I hope what we can see is we have some type of, if we ignore the spectator sodium ion, we have an alkoxide, an O, a negative O, negative oxygen. And then over here, we have kind of similar thing, but with a sulfur, right? That's the difference between these two reactions, right? This negative thing over here is what's different. We have the same, propyl chloride. We have the same ethanol over the arrow. And if you look overall, I'm hoping what you can see is we have a primary carbon. We have a good leaving group. We have a negative molecule, a nucleophile. And I think it's not a stretch of the imagination to say that what we actually have here is some SN2, because we can see that the sulfur comes in and bonds to this carbon right here, which would be this carbon over here, and same deal up top. So what's the thing that makes it different? What's the differentiator? Well, it's going to play into the fact that we have an oxygen and a sulfur in, both the above and below reactions. Now, what's the relationship between oxygen and sulfur? Recall that they're in the same column of the periodic table. Sulfur is bigger than oxygen. How does that factor in? Note the solvent in this case. Remember, so this is an SN2 reaction, right? Now, remember for SN2, we like polar aprotic solvents. We like solvents that do not have an electronegative atom directly bonded to hydrogen, right? We do not like OH. We do not like NH. Those are no-goes for us. However, you can see that our solvent ethanol here is in fact polar protic. So let's put it this way. We're looking for the faster reaction. So the fact that this is polar protic, how is that going to impact the nucleophile? What will that affect? The fact of the matter is that this hydrogen in the solvent is super, super, super partially positive. It will try to find anything negative and buddy up next to it. So what we have here is that the negative sulfur and the negative oxygen will experience a bunch of solvent. Let me use blue. A bunch of solvent coming up around it and just hanging out, creating what we call a solvent cage. So the fact of the matter is that oxygen being a smaller atom, it's going to get much more enveloped, much more crowded by a solvent cage than the much larger sulfur atom. So as a result, the sulfur atom will have less trouble getting to the substrate and actually executing SN2. So as a result, it is this reaction right here that will be faster due to the fact that the sulfur being larger in size handles the solvent cage better. So I'll just say handles solvent cage better due to S greater than O size-wise. That should be a sufficient explanation. All right, now let's play the same game but below, and not only but slightly different game because we're looking for the slower reaction. So if we digest this down here, what we're seeing is we have potassium hydroxide and we have ethyl iodide, and you can see again we're kind of doing another SN2 reaction. The hydroxide displaces the iodide leaving group in both situations. However, the thing that's different, maybe you picked up on this already, is our solvent yet again. Or sorry, not yet again. Up here, the solvent was the same, nucleophile was different. Script is flipped here. Same nucleophile, different solvent. So same size nucleophile, and remember, this is SN2. So normally for SN2, we like polar aprotic solvents. That helps things go faster, it helps the reaction kind of go on its merry way. But remember what the question is asking. Never forget to take your time reading the question or really understanding what it's asking you for, because we're asking for the slower reaction. So we want the worst case, environment for SN2. And just like we talked about up here with the solvent cage, the slower reaction will experience a solvent cage. So the methanol down here, which looks like this in terms of its chemical formula, methanol is polar protic. That is going to have a solvent caging effect on the hydroxide down here. That will slow down its progress getting to the ethyl iodide. This reaction will be slower than the reaction above because DMF is polar aprotic. It's a great solvent for SN2. And that, my friends, is problem 3. All right, let's move right on into problem number 4. Just gonna check the time really quickly. All right. Problem 4 is maybe what you've all been waiting for. Here's where we reach into and tackle a bunch of substitution elimination problems where I'm not telling you what it is. We need to just figure it out. So I have 6 of these. So we'll do 3, erase, do 3 more, and then move on to problem 5. Make this a little bit better. Okay. Okay, almost finished writing the 3rd. So we'll step through, a good process, a nice formulaic approach to figuring out what you need to do to kind of, digest the information here, figure out what type of reaction, SN2, SN1, E2, E1, and then correctly predict the product or complete the problem in however it's asked. Okay, so we have 3 problems right here. So the first of which, we have this molecule right here. We have our good old friend potassium terbutoxide, and we need to predict the product. Now, I feel like this first one leading off, anytime you see potassium terbutoxide and you can't find some type of proton to deprotonate or something like that, if you see let me rephrase it this way. If you see potassium terbutoxide and you have a carbon of any substitution level, whether that be primary, secondary, tertiary, and you have a good leaving group, this is screaming at you to do E2. I'm just gonna put that in brackets. That's not any type of formal reaction notation. I'm just trying to save space on the board. This is screaming do elimination. Potassium terbutoxide is big and bulky. It is also a nice strong base. So it can do elimination, and because of its size, it's so sterically hindered, it can't dream of doing SN2. So E2 is its jam. So now that we know what type of reaction it is, now we kind of need to move on into what are some extra quirks I need to consider and how can I predict the product. Remember that in E2, we take our carbon that has the good leaving group and we go next door to find a carbon that has a hydrogen to then rip it off and, take those electrons, form a double bond, kick off the leaving group. We have 2 options here. We have this option I'm going to asterisk, and then we have this option over here I'm going to put in a box. Remember that due to the size of potassium terbutoxide, it's big, it's bulky, It's lazy. It goes for whatever hydrogen it can get to most easily. This is a tertiary carbon with a hydrogen. It's a little crowded to get in here because this carbon is attached to 3 other carbons. On the other hand, this carbon over here is primary. It has 3 hydrogens. I'll only draw one of them. And it's much easier to get to this primary carbon and its hydrogen as opposed to this tertiary carbon and its hydrogen. As a result, if I'll draw the arrows mechanistically, let me just erase that a little bit. We'll do this. I'll put the potassium. Potassium doesn't matter, but it's there. Potassium terbutoxide will grab the hydrogen next door of the lesser substituted carbon that free the electrons up here to swing down, form a double bond. And as all of this is happening at the same very time, bond forming, bond breaking, we kick off our leaving group and break the carbon iodine bond. So in terms of what we would deem a major product, you would get the Hofmann elimination product, the product that results in the lesser substituted double bond. If you needed to draw both, if you needed to provide the Hofmann and what's known as the Zaitsev product, the minor would just be the one you would form over here. So if you ripped this hydrogen off and the double bond formed right here, this would be your minor product over here. So this is, people spell this all different sorts of ways. So if you spell it differently, don't worry, there's different spellings. And then I believe Hofmann is 1 F, 2 N's. Either way, this is your major product. This is what a professor would reasonably expect given these reaction conditions. And it's all because of how the size of potassium terbutoxide. Okay. So this was E2. Moving on over here, and the reason why I didn't provide a solvent is because when you see potassium terbutoxide, solvent or not, that's someone nudging you towards E2. That's a check I'm prepared to write, and you can take it to the bank. Okay, down here, some things that we have going on. I can always look to the solvent first. Here's like a good approach. Always go to the solvent. We have polar aprotic here. Now remember, our 4 options here are SN2, E2, SN1, and E1. SN1 and E1 like polar protic solvents, and SN2 and E2 like aprotic solvents. SN1 and E1 need the polar protic solvent to formulate a carbocation. So the minute you see polar aprotic, these don't matter anymore. They're not an option. I know we had an example earlier, but that was me telling you that SN2 is happening with a polar protic environment. So that wouldn't be like a major situation. So here we're either considering SN2 or E2. Now we have a secondary substrate, right? So this is kind of that in between. Could it be elimination, E2? Could it be substitution, SN2? It's going to depend on whether we have something that's a strong base or a weak base, because secondary is that in-between state. This OTS, this is a tosylate group. It's a good leaving group. If you're familiar with it, then this is probably no surprise to you, but if you haven't seen that before, just think of it as a big bromine or something. Very good leaving group. What we have here is the conjugate base of H2SE. So it's selenium, but in a, in an acid form. Just think of it as like H2S, for example, or H2O, because on a periodic table, we have oxygen, sulfur, and then selenium. So selenium is 1 row down from sulfur. So it's much bigger than sulfur. And as a result, what I'm getting at here is if we had H2O, H2S, and H2SE, the more rows we go down the periodic table, the bigger the atom gets. And as a result, the more acidic we get. So H2SE is a much better acid than H2S and is significantly more acidic than H2O. H2S, if you look it up, has a pKa of around 3.9. So its conjugate base, this is a strong acid, its conjugate base is heckin' weak. You might not have pKa values available in your exams, But if you just recognize that selenium is in this family, this column of the periodic table, and as you go down, size of an atom increases, then you will, that's your tip off that, oh, H2S can donate H plus much more easily because of, it comes down to the length of the bond here, which gets longer as an atom gets bigger. H2SC, very strong acid, conjugate base is weak. We're not doing E2 here. This is a substitution reaction because of the fact that this thing is a bad base. It is negative, so it's going to act more as a nucleophile. So now that we determined that this is SN2, what we can do here, I'm going to ignore the sodium. I'm just going to draw SEH. Since this looks like oxygen, it'll look like this. You can basically almost think of this as hydroxide, but just replace the oxygen with a selenium. And we will perform SN2. We'll attack from the backside. We'll eject our leaving group. I have 1, 2, 3, 4, 5 carbons. And it is on carbon 2 from the left-hand side that I have my SEH attached. And now remember, we attacked a stereocenter. This is SN2. We do have stereochemical inversion. So the leaving group was a dash. That means the SEH minus had to come in from the backside, which is a wedge. So when we bond, we are now attached as a dash. Cool. Now, continuing on down here. If we take a look over here, acetone is the solvent here, because if I take a look at KNH2 is either going to function as a nucleophile or a base. Acetone is a role player in terms of just being a solvent. And in terms of a solvent, it is polar aprotic. So, again, now that limits our options to either SN2 or E2 because we can't formulate a carbocation with a polar aprotic solvent. Now, when we take a look at the substrate here, I know there's a lot going on, but if we look at this carbon, we see that the a bromine is here because we have an ethyl group and a methyl group. The bromine is the leaving group here. So this carbon is our substrate carbon, and luckily what you can see is this carbon is 1, 2, 3. This carbon is tertiary. As a result, we have zero possibility of SN2 here. So, because being tertiary, we're too sterically hindered for any type of attack to happen. That means by default, this is going to be an E2 problem. Now remember, we kind of have to go into the whole big base, small base thing to make sure we can actually do E2 in the correct location. So, the base we have here is NH2 minus. I'm going to just, ignore the +1 potassium. Oh, whoa, that's not correct. There we go. We have NH2 minus, a small base. So unlike up top where we were lazy, we picked the easiest hydrogen to get the Hoffman, here we're going to, pick the hydrogen we would expect to form the Zaitsev product, the more substituted double bond. So if we take a look right here, this is a tertiary carbon, and so is this over here. This carbon, we would prefer a tertiary double bond over a tertiary secondary double bond, and prefer that over a tertiary primary double bond. So we ideally want to do this, we want to make the elimination happen such that we have the blue dotted line, but we have to check for one more thing. We have to check for the anti-periplanar requirement. So if I take a look at this position right here, the hydrogen available for elimination is on a wedge. The problem with that is the bromine is a wedge and the hydrogen is a wedge. So they both look like this. A wedge is kind of like up on a ring. They're on the same side. They are actually cis-periplanar to one another. We need something that looks like this. So because of the fact that this hydrogen is on a wedge and not a dash, we actually cannot perform the elimination there. It's just not possible. We need anti-periplanar to help set up the p orbitals for the double bond that's about to be formed. So because we can't do this, we go to the next best option, which is in fact down here because there's a wedged and dashed hydrogen on this secondary carbon right here. So we can't do this, so we default to this down here. Grab the wedged hydrogen, the electrons in the wedged hydrogen swing down, and we kick bromine off. Now we need to draw the product correctly. We have a ring. We didn't touch this ethyl group at all. So that just, feel free to redraw that. Now we have a double bond right here. And the last little trick about this problem is, in making this a bond right here, these two carbons go from being sp3 to sp2. We have to make sure this methyl group is present, but it's not a dash anymore because sp2 carbons don't have wedges and dashes. I need to draw this as a straight line. Okay, so that's your product there. This is, if at all this didn't make sense, revisit this, because this, if you can do this type of problem, you can handle pretty much anything thrown your way E2 wise, because this makes you check for, you know, where you should do the elimination, but you have to check for anti-periplanar requirement. Then you actually have to figure out that you can't do it here, so you do it here instead, and that you also kind of honor the new geometry that's introduced by doing the elimination. Okay, let's keep it going. Like I said, we have 3 more. All right. Nothing more exciting than watching erasing. Okay. Okay. Yeah, that's right. There's another Fisher projection here. I am sorry about that. Okay, so let's take a look right here. So we have 3 more problems for problem 4. And what we're going to do here in this first one, so hopefully when you look at what's over the arrow, you can see, you know, there's not, heat is the big thing provided, right? Delta meaning heat, or maybe someone would explicitly write heat. You see polar protic solvent and heat. When someone explicitly gives you heat and you have a polar protic thing present, you know, solvent present, this is screaming to you E1. If the heat thing doesn't sound like a familiar concept, watch my video on Geochem about why temperature favors elimination. It comes down to the Gibbs free energy equation. However, this is screaming to you, have an E1 major product. So E1 major is what we'll deal with. Now, when we do SN1 and E1, we have to be careful about carbocation shifts, right? Rearrangements. So the way I like to do this is that this solvent will facilitate solvolysis. So what I like to do, I'm going to erase this over here, is I like to just, you know, draw the initial resulting carbocation after our leaving group leaves, which would look like this. Okay? We have a secondary carbocation. You need to ask yourself and evaluate, can you make this better? Can you improve the carbocation by moving it next door by either a methyl shift or a hydride shift? Hydride shift being your first option because that's a smaller thing to move. And the answer here is yes. We are secondary here, but we are tertiary right next door. There's 1 hydrogen available. We can move that via a hydride shift. So what we really have is this carbocation. Right there. There we go. This right here. Now we can actually do the reaction we meant to do. In this case, E1. Now you want to form the most substituted double bonds you can, aka like the Zaitsev product. So this is tertiary. So we either have a tertiary secondary option, or, and what we'll do is tertiary. So it's not the best base in the world, but the heat provided helps. That's where you will get your ethanol solvent acting like this. It performs the elimination. Something will perform the elimination, and you will get that E1 major product. And if you have to provide both, right, let's just say, because you will form an SN1 minor here, right? You basically, instead of having this elimination happen, you'd have the ethanol attack instead. So we have this. Your ethanol would come in. The oxygen is the nucleophilic atom. You attack right there. No need for the leaving group to leave because it has already left through solvolysis. You would initially get, sorry, it looks like I'm limping because I'm just trying not to step on my, my mic cord. You would initially get this, but something will come along and take that hydrogen away, and you will end up with OET here. So let's be clear. You make both, but your major product would be the E1 because of the heat provided. Cool. So for this, E1. Now down here, if we take a look at our environment going on, we have a secondary substrate with a good leaving group, and bing, bing, bing. It's only one thing listed over the arrow, but what I hope you're seeing is that this is acetic acid, and I hope that you're honing in on this right here. This is I should write polar protic here, and this is also a polar protic solvent. So because it's polar protic, we're considering SN1 and E1. Because there's no heat, you can assume it's going to be an SN1 major product, okay? So again, same game. Let's make sure we identify our carbocation and evaluate if there will be any shifts in that carbocation. So if I have the iodine leave, then I have this left over, and this looks like it might shift. However, there's one carbon in between this secondary and tertiary position, so we're gonna leave this stay put. It's just gonna stay where it is, okay? Now, it's as weird as it is, our nucleophile will come in and do an attack, and what that nucleophile is the acetic acid. So the acetic acid will attack right here. So what we get initially is this. I didn't touch this at all. And now here's the kind of the little quirk with this problem is when we have this carbocation, it is trigonal planar, sp2. It's flat. So when this acetic acid nucleophile comes in, it can either attack from the top as a wedge or the bottom and connect as a dash. It doesn't have we can't guess what it's going to do. So what we can safely assume is that it's going to happen about roughly in equal amounts. So I would I wouldn't just recommend. What it will happen here is you will have two products, one as a wedge and one as a dash in terms of just connecting at this position right here. Then I'm going to dot. Now, the thing that actually attacked was the oxygen in the kind of OH part of our carboxylic acid. So we have this right away, O with an H, and then just draw the rest of what it's attached to. A line to a carbon with a double bonded oxygen and another carbon, and the same thing over here. And initially, you'll have a plus charge. I would draw this over here, but I'm running out of room, like board space. So you'd have this. And before you kind of draw your final answer, Something will come by and clean this up to get rid of that oxygen's formal charge, because we know oxygen doesn't love formal charges. It could be another one of these. It could be the iodine. Something in solution will kind of take care of that. So just make sure, again, if you really wanted to, well, that's okay. I'm just going to, for the sake of the board space, these would be your final answers. The cleanup would happen after the fact. These would be your final answers. And one thing that's important to note is that when you do SN1 and you attack a position that turns into a stereocenter, at that stereocenter you do get a racemic result. But that doesn't guarantee that the structure overall, you won't get a racemic mixture overall, because you can see here, these are not enantiomers, these are diastereomers. Just because this stereocenter stayed the same. It was uninvolved in the reaction. Okay, last one for problem 4. I gave you the reactant and the product, and you actually need to tell me the middle. You need to tell me the step or steps over the arrow, the reagents that can power this reaction. And I gave you a hint because I'm a nice guy. 2 steps. So hopefully what you're seeing is that the ethyl on both sides is in the same position, so is this methyl, and so is this hydrogen. The thing that's changed is the bromine here. With this group over here, we have it's called a nitrile, but it's a cyanide group attached. Remember about Fisher projections. When this is a wedge, right? We can even do this to make this a little bit more obvious. So we've done a replacement of the bromine, but we know that in SN2, you invert stereochemistry. So how do we end up just clean replacing it on the same side, the same side, if you will? That's why we need 2 steps here. If one SN2 reaction inverts stereochemistry, then just like the double switch, 2 back-to-back SN2 reactions would invert and then recover the stereochemistry. So in your first step, I would just draw a little 1 with a dot or whatever. If you threw something in like sodium iodide or potassium iodide, some good nucleophile, you would, if I drew this over here, have the I- attack here, kick the bromine off, and you would have this. Iodine on the left, methyl on the right, ethyl down low, hydrogen up top. We have effectively switched a pair of groups and we've inverted stereochemistry. And that helps us because what it sets up is for us to kind of throw in sodium cyanide or KCN, potassium cyanide, because what that does is that brings now in CN-, which is also a good nucleophile. It can attack the carbon. It can boot off the iodide. And what we have is the result. Cyanide would flip the stereochemistry, end up on the right-hand side. Methyl group goes back on the left. Boom, problem solved. Okay, gang, I tried to pick a variety of like these SN2, E2, SN1, E1 problems because trust me, I sucked hard at this stuff when I learned it. If you get a process that you like, look at the solvent, always trust in the solvent, digest the information in a way where it's very procedural. You can kind of like, pick out the meaning. It really does simplify a lot of these problems. Okay, so, and I think I lied to you. I actually have, because I consolidated a little bit, we have just 2 more problems. We're gonna go to 6. All right. Let's keep erasing. This one might unfortunately involve me drawing a little bit, so I'm gonna try and do this as fast as possible. So a good time to check Twitter, Instagram, TikTok, what have you. 5. So what we have here is okay. So given this reaction here, and there would probably be some, residual other stuff like some other stuff, but we're just concerned about the organic product. I'm going to give you a sequence of 4 energy diagrams, and this is what's going to take me a minute to draw. Okay, there's 1, 2, we got 3, we have 4, we got 1 more to draw. Okay, cool. So, given this reaction up top right here, we need to pick the energy diagram that corresponds to the reaction I've shown you up above. Now, the trick here is that you need to know how this reaction works to inform your decision of the energy diagram, because what we've seen when we do mechanisms is kind of like one step corresponds to an energy bump, right? Or like an activation energy, a beginning state and a final state. So what I'm hoping you see in this reaction is clearly we have this chain kind of wrap on itself and cyclize to form a ring. So what we can do here is we don't have any type of, so hopefully what it makes sense is that we have 1, 2, 3, 4, 5, 6. We can see that the oxygen kind of needs to make another bond with a carbon, and it is 1, 2, 3, 4, oops, I can't count, 5, 6. It itself is, one of 6 atoms in a chain of 6, where if it wrapped around and attacked this carbon, which also conveniently happens to be attached to a leaving group, we could actually perform this type of cyclization. However, this oxygen isn't super nucleophilic in its current state. But if you notice the KNH2 over the reaction arrow, we luckily have a strong base on our hands. So what we're going to do here is 2 steps, essentially. The first of which I'm going to cheat to save space, and I'm going to actually wipe this away. Step number 1 is our NH2 minus, which I'm going to redraw over here, just NH2 minus. It will deprotonate the oxygen right here. So I'm going to draw our step arrows in blue. One, 2, 3, 4. Sorry, I'm running out of space, but you can see all we did from here to here is that the OH ditches the hydrogen. 1, 2, 3, 4, 5, 6. At this point, we have a much more nucleophilic oxygen. We have an alkoxide. It does this, which will create a 1, 2, 3, 4, 5, 6-membered ring with the oxygen being at position number 1. And for this attack to actually work, which is an intramolecular reaction within the molecule, we can boot the chlorine off, the chloride. And what you can see is if I number around the ring, I can say oxygen at position number 1. Oh, I can draw the blue arrow. Oxygen at position number 1, nothing at 2, nothing at 3. Oh, methyl group at 4, 5, and 6. That supports our reaction. So what we need to do now is, looking at our array of energy diagrams, we need to pick 1, 2, 3, and 4. Which one actually corresponds to the mechanism we just drew? Right? Draw the mechanism, pick the diagram that reflects it. So here's a nice quick way to eliminate a bunch of your options. We only have 2 steps here: the deprotonation and the attack. So right off the bat, if you see a diagram with 3 humps or 1 hump, or any diagram without just 2 humps, we can immediately eliminate these, because we should have 2 humps based on the deprotonation, 1, and the attack, 2. One for every blue arrow, essentially. Now down here, we need to pick the correct diagram. Now here's the thing, is that this reaction, which starts off with an acid-base reaction, acid-base reactions are the most favorable thing you can do in organic chemistry. They're super fast, they're super, they give off heat, they're always trending towards stability. If you look at number 2, in this first step, which would be the acid-base step, we actually end up starting at one energy level and then going up in energy. This means we would go from less stable to more stable to less stable, higher in energy, more reactive. On the other hand, with 4, we go from higher energy to lower energy. And you can see that we both have a big energy drop for the attack in both scenarios. This is inaccurate. Acid-base reactions are favorable. This is trying to say that we would have an endothermic change, and that's not the case. This very accurately illustrates what's going on here. That is the proper energy diagram that shows a quick and dirty little favorable acid-base reaction followed by the much more, big exothermic intramolecular SN2 reaction that goes on here, okay? That was 5. We got one more, gang. Stick with me. Doing good on time as well. All right. So this last one is a bit more of a, maybe you've gotten to synthesis in your class yet, maybe you haven't. If you haven't, do not sweat it. This was kind of me trying to include a type of problem in case someone's watching this and is hoping to see something that is, more synthesis geared, or they're, just ahead of the material that I'm covering here, AKA like on alcohols or something like that. So what I want to do here is show that if we start off with an unlimited supply of propane, how can we, with the reactions that we know, create this molecule right here? Okay, so this is what's called a synthesis problem, where you basically just string a bunch of reactions together to go from the starting material you're told you can use to a target molecule, a target product. Sometimes you will also see this notation, these multiple arrows with a question mark. Sometimes you'll end up seeing target molecule with a big block arrow like this, meaning go backwards. However, since you may be new to synthesis, I'm going to show it like this. Just know either one is valid. So we can use as much of this as we want to make this. So here's the strategy I like to use first. We can use as much propane as we want, and like other, like any type of reaction that we know, free radical chain reactions. We can grab sodium hydroxide if we need it. This is our only source of carbon though. I like to look at my target molecule and count up all of the organic atoms, AKA the carbons. I have 1, 2, 3, 4, 5, and 6. So we have 6 total carbons in our target product, which to me says, since we have units of 3, we are going to need 2 propanes. And we're basically going to need to smush them together, okay? So, as weird as it sounds, there's an approach called retrosynthetic analysis, which means start at the end and work backwards. That's what I'm going to do here. It's totally weird. It feels uncomfortable at the beginning. I promise you, it is definitely the way to go. So, and here's what I mean by that. I'm going to draw an arrow that goes like this. It's a long one, but it's really just a bent reaction arrow. And this is basically going to say, if I'm starting at the end, and let's just say I had to come up with whatever created this going forward, what would it look like? What 2 things would it look like? Right? What would these 2 boxes be to support creating this? And hopefully this makes sense to you. that the only way we know how to kind of put pieces together is by, substitution. SN2, SN1. And in this particular case, I'm going to say, let's use SN2. We don't want carbocations. We don't want the potential for rearrangements. Let's just do SN2 and, just do a nice clean attack and kicking off of a leaving group. Now remember, what do we like for SN2? Good nucleophile, good leaving group, polar aprotic solvent, and low steric hindrance. I'm thinking that this oxygen will be an O- somewhere, right? The question is, do I make an imaginary cut right here in blue, meaning this 3 carbon section got attacked by the oxygen and this thing over here? Or do I do a black squiggly and have this thing attack this carbon right here? So I'll put a dot over here and I'll put an asterisk right here. Hopefully what you're seeing is that the asterisk carbon, number 3, that is, if I were to pretend this didn't exist, this would be a primary carbon. That would be great to get attacked SN2 wise. If I did play the opposite game, number 4 would be secondary. And if this, if I'll actually draw it out. We have this and we can have this. I'll use X as a leaving group, some halogen, or we can have this. These are our 2 options based on what I was trying to do with my hands covering them up. I'm hoping what you're seeing is that we would rather attack a primary carbon over a secondary carbon, because if we did the secondary case, we might have some unintended E2 product. We might accidentally do some elimination. So what I'm going to do is this is 3 carbons with an O- in the middle. That's this right here. This is what we're going to go forward with. Oh, I'm so sorry. This one right here. So not this. And then we will have 3 carbons and some type of halogen, because we know halogens are good leaving groups. Because by doing this, I'm gonna erase this now. There's no reason why I drew 1 in black and 1 in blue, by the way. What we can do now is we have 2 smaller problems. Now I need to make this from this and this from this. But now I just have units of 3 carbons. So what I can do now, let's just take care of this one right here. Luckily, I'm going to draw an arrow straight from here. We have reactions to put halogens on carbons, right? We can do free radical chlorination or free radical bromination. And I'm going to actually redraw this to be a little bit more kind of like it appears up there. I just need 3 carbons and the halogen on the end. Remember that bromine is the much pickier one. If I did free radical bromination, I would put a bromine on the secondary central carbon. So if I just did Cl2 and light, that means I would reasonably expect a good yield or a good enough yield to put a chlorine on one of these end carbons. So I could actually change this X to a concrete Cl. And what you've effectively done is you've connected the dots here. We've shown how this gets made. Thumbs up. Now we need to just kind of connect the rest of the story back up here. So we'll kind of draw another one of these arrows back. I'm just going to use my space. It's an art. It's an art, not a science, in terms of how you draw these arrows in a synthesis problem. So feel free to bend them, curve them, however you like. We don't know how to just kind of create an O- from nothing. But if I had this look like OH, if I threw in NaNH2, for example, that would be a strong base that would just deprotonate this, just like in the last problem, and create O-. So this would work. Now, what we can do is, like we said up here, and I'm kind of jumping backwards, but we know I could stick something on the middle carbon up here. If I did Br2 light and heat, that would give me a bromine up top. The reason I'm doing that is because I need to somehow get an oxygen on here, an OH. And we don't know how to put an OH on directly. But if I put a bromine on here, what I can do is I have two options. I can either do NaOH and attempt SN2, maybe get some E2 product, or because there's no risk of a carbocation rearrangement, I can do H2O. What the H2O will do is it will facilitate solvolysis. Luckily, no carbocation shift will happen. I'll bring in my H2O. It will attack. At first, I'll get this, OH with a plus. I can reasonably expect another water will clean this up. And I'll get this up here. You don't need to draw this mechanism in the synthesis problem. That was just me showing you all of the steps in between. So a synthesis problem is basically taking all of the reaction knowledge you have, not showing the mechanism unless you really want to draw it, but I would recommend drawing a mechanism in a problem and then erasing it, more of just like verifying what you're doing if you're unsure. Just stringing together all the reactions you know to build building blocks to ultimately build to one unified final building block. Whew. Okay, gang. Thank you for rocking with me for 76 minutes. I hope this review was helpful for you. It will be available on YouTube and JoChem after the fact. I'm going to put like chapters in it. So if you watch it on YouTube, you can hover across the bar and see the individual, problem sections. I really appreciate you tuning in. If you're a geochemist, thank you for, I'm glad and hopeful that GeoChem is helpful for you in your organic chemistry journey, in your quest to conquer carbon. Thank you so much for being a geochemist. Thanks so much for watching. Tell a friend, subscribe, like, all the good stuff. And no matter what, I hope to see you all in the next video.